Aloha biostatisticians. I am pre-recording today's lab for you so that you can walk through it at your own pace. Start by opening the R notebook that I sent you called Multiple Linear Regression Lab cars.rmd. When you open it, it might prompt you to install packages with a line on the top in yellow. If so, do that. Install the packages. I'm going to go through this lab kind of fast, but because you'll have a recording, you can go through it at your own pace, okay? So once you have it open, go to the title. You'll see this, Multiple Linear Regression Lab, CARS example, right? And you'll see author, a student. Type your name here, right? Then type the date. If you're doing this in class with Michelle and I, we can help answer questions for you, or you can do this on your own. I recommend doing it before class if you want to do it on your own though, so that if you do run into problems, you can come to class and get help. If you're doing it tomorrow, the date will be 3.14.24, which is Pi Day. For this lab, we're going to talk about sustainability and transportation using the CARS analysis. For this study, we'll imagine we are sustainability consultants tasked with finding ways to steer the transportation sector towards carbon neutral. We might begin by looking at the existing fleet of cars produced and asking what factors are related to fuel economy and how. We will begin by reviewing simple linear regression, SLR, and then move on to more complex analysis with multiple linear regression, MLR. Be sure to answer all the questions marked with a forward-pointing arrow symbol and submit your notebook as an HTML or Word file to Lalima. To review the principles of multiple and simple linear regression, first of all, simple linear regression, or SLR, is a statistical approach that allows us to assess the linear relationship between two quantitative variables. More precisely, it enables the relationship to be quantified and its significance to be evaluated. 2. Multiple linear regression, or MLR, is a generalization of simple linear regression in the sense that this approach makes it possible to evaluate the linear relationships between a response variable, which is quantitative, and several explanatory variables, which can be quantitative or qualitative. Multiple linear regression is used to assess the relationship between two variables while taking into account the effect of other variables. By taking into account the effect of other variables, we cancel out the effect of these other variables in order to isolate and measure the relationship between the two variables of interest. This point is the main difference between simple linear regression and multiple linear regression. Data. For this example, we use the mtcars dataset, which is preloaded in R. This avoids problems with loading our own data. So to load the data, simply run this chunk, either by having your cursor on the line with the code and pressing either Control for a PC or Command for a Mac, Enter. Control Enter runs the code, or you can go to the upper right-hand corner of the chunk and press the green play button to run current chunk. Does the same thing, except run current chunk runs all the lines in the chunk, and having your cursor on the line, or if the line is highlighted and pressing Control Enter runs just that line. As soon as you run it, you see in the upper right hand corner under data that we have now created an object called DAT, which has 32 observations of 11 variables. If you click on the blue circle with the little white arrow, it opens up a drop-down of all the variables that we have in this data set. Miles per gallon, cylinders, dispersion, horsepower, etc. And you can see that all of these 11 variables are numeric. If you click on the name DAT, it opens up on the left a new tab showing a spreadsheet of the data. Miles per gallon, cylinders, etc., and the names of each car that was measured. You can also use this spreadsheet to sort the columns by clicking on the up and down arrows, sort by smallest to largest, or sort by largest to smallest. It's a pretty handy feature in RStudio. Going back over to the tab for multiple linear regression with the code, scroll down to where it says data structure. Running this structured data command basically shows us the same thing that we got from looking at the window on the upper right. It shows us that we have a data frame with 32 observations of 11 variables and the names of all the variables and the data types of all the variables. Again, they're all numeric. Scrolling down to summary statistics. If we run this command summary dat, we get a handy output that shows us a summary of all the variables. There's the 5-number summary, minimum, first quantile, median, third quartile, and max. It also has the mean for all the different variables, miles per gallon, cylinders, dispersion, etc. If you scroll down to the next chunk, you can run this command head dat, and you get a snapshot of just the top several rows of the data. Now answer these questions on your own. How many variables are there? Just look over here, right? What is the mean miles per gallon of cars in the data set? Scroll up to the summary statistics and find the mean miles per gallon. What is the range of cylinders? Scroll up to the summary statistics, look at cylinders, minimum 4, maximum 8. How many cars are included in the data? Well, how many observations are there? Hint over here. What are 3 brands of cars included in the data? Again, look at the head or the data, and you can see, just choose any 3 brands. Be sure to answer the questions in complete sentences for full credit. How many variables are there? There are X variables in the data. Complete sentences with capitalization and punctuation, please. Next, we'll scroll down and review simple linear regression. To begin, let's briefly review simple linear regression. We'll examine the relationship between car weight and miles per gallon, or MPG. Our Y variable is the variable considered to be the response variable, or the variable to be explained. It is also called the dependent variable and is represented on the y-axis. X is the other variable in the explanatory, or called independent variable. Sorry, let me say that again. X, the other variable, comma, X, the other variable, is the explanatory, also called independent variable, and is represented on the x-axis. The first thing we want to do is make a quick scatter plot of the data so we can see what it looks like. Running this chunk, we can make a plot. Notice that we're going to use this library, ggplot2, which you should already have installed. This command loads the library, and that allows us to use the function ggplot, which first asks, well, what's the data set? Dat. Then the aesthetic is where we specify the x variable, x in this case weight, and the y variable, y in this case miles per gallon. Plus, we want to make sure that we're including the geom of points, because we want to see points for the scatter plots. Plus, we want to see nice labels. The y-axis label will be miles per gallon. The x-axis label will be cars weight per 1,000 pounds. And plus theme minimal, which removes some of the extra shading that you get with the default ggplot. To run this chunk, press the green play button and scroll down to see, I'll minimize this window, we see more. We see a graph of the data, cars weight on the x-axis, miles per gallon on the y-axis, and we can see that there is what looks like a pretty nice linear relationship. These questions are all pretty easy. They're for you to just answer based on reading what I've already told you here, very little calculation, and a little bit of thought at the end. In the above graph, which is the response variable and which is the explanatory variable? Remember to answer the question in a complete sentence. Then, is the relationship between miles per gallon and car weight positive or negative, which you can tell by looking at the graph. Simple linear regression can be seen as an extension of the analysis of variance, or ANOVA, and the student's t-test. ANOVA and t-test allows us to compare groups in terms of a quantitative variable, 2 groups for the t-test and 3 or more groups for ANOVA. Linear regression is an extension because in addition to comparing groups, we can also use it with quantitative independent variables, which is not possible with the t-test and ANOVA. Hypotheses. For a bilateral test, the null and alternative hypotheses are: the null is that the beta 1 is equal to 0, or the slope of the x variable is equal to 0. That is another way of saying there is no linear relationship between the two variables. The alternative hypothesis is that beta 1 is not equal to 0, or that there is a linear relationship between the two variables. Scroll down to review the assumptions of simple linear regression. 1. Linearity. That means the relationship between the two variables should be linear, at least roughly. For this reason, it is always necessary to represent graphically the data with a scatter plot before performing a simple linear regression. 2. Independence. This means all observations must be independent from each other. It is the sampling plan and the experimental design that usually provide information on this condition. If the data come from different individuals or experimental units, they are usually independent. On the other hand, if the same individuals are measured at different periods, the data are probably not independent. 3. Normality of the residuals. For large sample sizes, confidence intervals and tests on the coefficients are approximately valid whether the errors follow a normal distribution or not, a consequence of the central limit theorem. For small sample sizes, residuals should follow a normal distribution. This condition can be tested visually via a QQ plot and or a histogram, or more formally via the Shapiro-Wilks test, for example. 4. Equality of variance. The variance of the errors should be equal. This is also called homoscedasticity of the residuals. There is a lack of homoscedasticity when the dispersion of the residuals increases or decreases with the predicted values or fitted values. This condition can be tested visually by plotting the standardized residuals versus the fitted values, or more formally via the Brush-Pagan test. Number 5, no influential points. If the data contain outliers, it is essential to identify them so that they do not, on their own, influence the results of the regression. Note that an outlier is not an issue per se if the point is in alignment with the rest of the regression line because it does not influence the regression line. It becomes a problem in the context of linear regression if it is substantially influencing the estimates and in particular the slope of the regression line. This can be tackled by identifying outliers via the Cook's distance or the leverage index, for instance, and comparing the results with and without the potential outliers. Do the results remain the same with and without the outliers? If yes, the outliers are not really an issue. Tip: remember the first 4 conditions with the acronym LINE, L-I-N-E, for L, linearity, I, independence, N, normality, and E, equality of variance. Scroll down to the regression equation. The regression equation can be written as y is equal to beta 0 plus beta 1x plus an error term. Y is the dependent variable, X is the independent variable, beta 0 is the intercept, which is the mean value of Y when X equals 0, also sometimes denoted as alpha. Excuse me. B1 is the slope or the expected increase in Y when X increases by 1 unit. E is the residual, the error term of mean 0, which describes the variations of Y not captured by the model, also referred to as the noise. The sign of the slope indicates the direction of the line. A positive slope, beta 1 greater than 0, indicates that there is a positive relationship between the two variables of interest. That means they vary in the same direction. Whereas a negative slope, beta less than 0, means that there is a negative relationship between the two variables, or they vary in opposite directions. This is similar to the correlation coefficient, which gives information about the direction and strength of the relationship between the two variables. To perform a linear regression in R, we use the LM function, which stands for linear model. In this function, we first specify the dependent variable, then the independent variable, separated by a tilde. So to run the linear model, scroll down to the next chunk and run a linear model on miles per gallon, which is the Y variable, versus weight, which is the X variable. So again, this is specified as LM, linear model, miles per gallon, which is the Y, tilde, weight, which is the X, and then specifying after a comma, data equals, in this case, stat. And we'll save all of the results of this model in something called model. We'll create a new object called model. Run this code, and you will see in the upper right-hand corner, let's minimize dat here, we'll see that we have created a new object called model. If we expand this model, we see that it contains a number of different things. In fact, it's a list of 12 different data frames and 12 different objects are contained within that list. Coefficients, residuals, effects, ranks, fitted values, etc. To view the output of the model in the form that makes it easy for us to interpret, we come back over to the next chunk and run this chunk called summary model. This gives us this, by now, somewhat familiar output. It starts by saying call LM formula equals miles per gallon as a function of weight on the DAT data. Great, that's what we told it to do. It then, for me anyway, gives me the residuals. I know some people don't get this in their output if they're using a different version of R. The minimum, the first quartile, the median, the third quartile, and the max of the residuals. I like to check this real quick and see if the residuals seem to be approximately symmetrical. For example, here we have a minimum of -4 and a maximum of 6. These are approximately symmetrical. I mean, they're not crazy off. It's not like -4 and 60, right? These are numbers that are fairly close together. That gives me a good indication that the residuals are probably more or less normally distributed or not highly skewed. Then we come down to the coefficients. We start by looking at the estimate of the intercept, which is our beta 0. The intercept here is about 37. We have the standard error of the intercept, the t-value, and the p-value of the intercept. Coming down to the next line, we can see weight. That's our x variable. The estimate for weight here is the slope. This is the beta 1. This is the amount that miles per gallon changes for every 1 unit change in weight. Remember, 1 unit in this case is 1,000 pounds. So for every 1,000 pounds that a car increases in weight, the miles per gallon decreases by -5. We also have a standard error for this slope estimate. And if you divide the estimate by the standard error, you get a t-value, which in this case, the absolute value of the t is greater than 2, which means we're very likely to have a significant effect. And in fact, we do. We have a very small p-value. It is 1.2 to the negative 10. Very small p-value. 3 stars, that means it is less than 0.001. We also get a residual standard error, which is 3.046 on 30 degrees of freedom, and a multiple r squared and an adjusted r squared. Looking at the multiple r squared, we can see that it is 0.7528, which says that approximately 75% of the variation in y can be explained by x. So 75% of the variation in miles per gallon can be explained by weight. Cool. To test the significance of the overall regression, we get an F statistic, which is 91.38 with 1 and 30 degrees of freedom. The p-value for the overall regression is, again, less than 0.001. The results can be summarized as follows. The intercept, beta 0, of 37.29 indicates that for a hypothetical car weighing 0 pounds, we can expect, on average, a consumption of 37.29 miles per gallon. But as a car weighing 0 pounds is impossible, the interpretation has no meaning. In practice, we would therefore refrain from interpreting the intercept in this case. The slope, beta 1, is equal to negative 5.34, which indicates that there is a negative relationship between the weight and the distance a car can drive with a gallon of gas. This was expected given the negative trend of the points in the scatter plot shown previously. But more importantly, a slope of negative 5.34 means that for an increase of 1 unit in the weight, that is, an increase of 1,000 pounds, the number of miles per gallon decreases on average by 5.34 units. In other words, for an increase of 1,000 pounds, the number of miles per gallon decreases on average by 5.34. Now, up to you to decide this. By about how much does miles per gallon decrease when the weight increases by 2,000 pounds? Get out your calculator and figure that out. You could probably just about do it in your head. Remember to answer in a complete sentence. Pause the video if you want to, otherwise I will continue on here. Significance of the relationship. The value of the slope does not, by itself, make it possible to assess the significance of the relationship. In other words, a slope different from 0 does not necessarily mean it is significantly different from 0 because there is always error associated with the estimate. So it does not mean that there is a significant relationship between the two variables in the population. There could be a slope of 10 that is not significant because of very high error, and a slope of 2 that is significant. To assess the significance of the linear relationship, we divide the slope by its standard error. This ratio is the t-test statistic and follows a student distribution with n minus 2 degrees of freedom. Roughly speaking, if this ratio is greater than 2 in absolute value, then the slope is significantly different from 0, and therefore the relationship between the two variables is significant, and in that case, it is positive or negative depending on the sign of the estimate of beta 1. The standard error and the test statistic are shown in the column standard error and t-value in the table coefficients. And you scroll up, you see standard error and t-value here in our coefficients table. Okay, your next question is, what is the standard error, test statistic, and p-value of the weight coefficient? All you have to do is go back up to the results and pull out the standard error, t-value, and p-value of the weight coefficient and write a sentence telling me what those are. Not here. Here. Tell me what those are. Then I'll scroll down to the conclusion for our simple linear regression. We get a lot of information from the linear regression output. Pay attention to how we can phrase it in words in our conclusions. For example, this would be an okay answer. There is a significant relationship between a car's weight and its fuel consumption. But that doesn't tell us very much, does it? What about the answer below? This is a way better answer. Car weight is a significant predictor of fuel consumption, explaining 75% of a car's fuel economy. And then we can say F statistic, degrees of freedom 1, 30, is equal to 90.38. P-value less than 0.001 and R-square 0.75. Indeed, the fuel consumption of cars in our sample decreases by 5.34 plus or minus 0.55 standard error miles per gallon for every increase in 1,000 pounds of car weight. Thus, finding lighter materials with which to build cars could potentially reduce carbon emissions from the transportation sector and have a positive environmental impact. Bring it home. All right. That's the kind of answer I like to see. Please use this as a model for your answers. Now let's make a scatter plot with shaded errors. First, we're going to load this library visreg and then run visreg model. And what this does is it shows us a quick scatter plot that also shows standard errors shading around the regression line, which gives us an idea of the amount of certainty we have of this particular slope. We can actually see that our standard errors increase a little on the low end of weight and on the high end of weight, and are narrower on the middle end of weight. You can also see we have more points in the middle, so we have less information on either side, which means that the amount of error we have is higher. We have less information from which to make these estimates. Also, the variance is higher. Yeah, I guess it's not really because of the number of points, but usually that's what happens. Okay. Then to make a much better graph, let's load the necessary library. In this case, we're going to use library ggpubr, which uses ggplot and adds a few bells and whistles. So we use the ggplot command, and again, we start by specifying the data, then specifying the aesthetic, which is where we tell it our x is weight and our y is miles per gallon. Plus, we want to add geom smooth, which adds the line, and we want to use the method linear model. We also want to add points using geom point, plus we want to add nice labels with, again, our y label being miles per gallon and our x label being car weight 1,000 pounds. Plus, we want to add some text into the graph that shows the regression equation and the R-squared, and again using the minimal theme. Run this whole chunk to come up with a graph that gives us the scatter plot, the regression line, the shaded error values, the regression equation, the R-squared, and nice labels for car weight and miles per gallon. This is a very pro-looking plot. It gives us a lot of information. Scrolling down, once again, I like to remind you that correlation does not imply causation. It doesn't. Be careful that a significant relationship between two variables does not necessarily mean that there is an influence of one variable on the other, or that there is a causal effect between these two variables. Scroll down, and we will begin now on the section for multiple linear regression. Background. What factors explain a car's fuel consumption? We saw that a car's weight negatively affects its miles per gallon, but what other factors could explain a car's miles per gallon? To explore this, we can visualize the relationship between a car's fuel consumption together with its weight, horsepower, and displacement. Engine displacement, by the way, is the combined swept or displaced volume of air resulting from the up and down movement of pistons in the cylinders. Usually the higher, the more powerful the car. So higher displacement, more power. And here I'm asking you the question, what do HP and displacement stand for? Yes, I'm just checking to see that you actually read the paragraph above the question. By adding information on the horsepower and displacement, we are able to capture only the direct relationship. Right. By adding information on the horsepower and displacement, we are able to capture only the direct relationship between miles per gallon and weight. The indirect effect due to horsepower and displacement is canceled out or adjusted for. So after accounting for horsepower and displacement, we can now find out what's the effect of weight. This is the whole point of multiple linear regression. In fact, in multiple linear regression, the estimated relationship between the dependent variable and an explanatory variable is an adjusted relationship, that is, free of the linear effects of the other explanatory variables. This allows us to take those lurking variables and account for them. Scroll down to the question. State the question in plain language. How would we state the question that we want to ask using these data? Think about it and write a good answer in a complete sentence. Then come down here to hypotheses. The hypotheses are the same as for simple linear regression. That is, the null hypothesis is that the beta of each x is equal to 0. And the alternative hypothesis is that the beta of each x, or bj, is not equal to 0. And the test of betas is equivalent to testing the hypothesis, is the dependent variable associated with the independent variable studied at a constant level of the other independent variables. In other words, we're essentially testing these 4 different hypotheses simultaneously in addition to testing the significance of the overall regression. So we can think of it this way. The test of beta 1, our first x, corresponds to testing the hypothesis, is fuel consumption associated with the car's weight at a constant level of horsepower and displacement? Second, the test of beta 2 corresponds to testing the hypothesis, is fuel consumption associated with horsepower at a constant level of weight and displacement? 3, the test of beta 3 corresponds to testing the hypothesis, is fuel consumption associated with displacement at a constant level of weight and horsepower? For the sake of completeness, the test of beta 0 corresponds to testing the hypothesis, is miles per gallon different from 0 when weight, horsepower, and displacement are all equal to 0? Scrolling down, let's think about how to write the equation. Multiple linear regression models are defined by the equation y is equal to beta 0 plus beta 1, which is the slope of your first x, times the value of x, plus beta 2, the slope of your second x, times the value of x, whichever value you choose to put in, plus as many more betas and x's as you want to put in, plus the error value. We often don't put in the error value because we don't really know how to add that in most of the time. We just say, okay, well, if we want to make a prediction, we can plug our variables into this equation and come out with a predicted y. It's very similar to the equation for simple linear regression, except there is more than one explanatory variable. So write the regression equation for this analysis using the model above. Remember to say, instead of y, what's our y variable? Miles per gallon, right? equal to beta 0 intercept plus beta sub 1 should be beta sub weight plus x plus weight, sorry, times weight. Let me write the beginning. Miles per gallon is equal to, I'm just going to copy this beta here. Well, I'm going to write this here. Intercept is equal to the intercept plus beta 1 is the beta of weight times whatever that weight value is, right? Plus, and so on and so on. I'll let you fill in the rest. Weight, displacement, horsepower, right? Then we'll scroll down, pause the video so you can finish writing that equation, and then when you're ready, scroll down to assumptions. And here I've just included the acronym for you to fill in. LINEO. What does that stand for? Remember from above? Linear, independent, normal, residuals, equality of variances, and outliers not with strong influence. For multiple linear regression, we add another assumption, another condition, and that is independent x's, or no multi-collinearity. This means that when the explanatory variables are strongly correlated with each other, we call it multi-collinearity. It is important to check it because it may lead to an imprecision or an instability of the estimated parameters when a variable changes. Check it by running the correlation between each pair of independent variables, or even better, by computing the variance inflation factor, or VIF. The VIF measures how much the variance of an estimated regression coefficient increases relative to a situation in which the explanatory variables are strictly independent. Right? We're seeing how much variance increases, how much it is inflated relative to a situation in which it was strictly independent. A high value of VIF is a sign of multicollinearity. So what's high? Well, VIF equals 5 is moderate. VIF equals 10 is high. Anything higher than that is definitely cause for concern. The easiest way to reduce VIF is to remove some correlated independent variables or to standardize the data. Standardizing the data is a way of transforming the data that we will review in a future lab. So let's scroll down to look at our Model 2 for multiple linear regression. Simple as this, linear model is the function on our y, miles per gallon, as a function of tilde, our first x, weight, second x, horsepower, third x, displacement. What data? Dat. And we'll take all this and we'll store it in something called Model 2. Run this chunk, and we have now created, if we minimize Model 1, we can see now we have Model 2, which is also a list of 12 things inside. I'm not sure what they're called inside. Okay, checking model assumptions. Checking model assumptions might be the very hardest part, but we can do this. We can do this. I'll walk you through step by steps. Let's start by installing the car package. If you haven't already done this, you should have already done this, but if you haven't, do it now. I have a little hashtag here so that when you go to run the whole chunk or knit it, you don't have to install it every time. You can even delete this line because once it's installed, it's on your machine. You just have to load it by running the library car function, right? Loading required package, great. And this will allow us to easily check several of the assumptions. First, we're going to check the linearity of residuals using the crplots command on the results of our model 2. Running this line, we get component and residual plots for each one of our x variables: weight, horsepower, and dispersion. Dispersion? What is this thing called again? Displacement. What I know about cars, you can put in my eye and it wouldn't hurt a bit. Weight, horsepower, and displacement. Okay, what we're looking for here is that the solid purple line should be close to the dashed blue line. I hope that you also get blue and purple lines on your computer. That's what I get on mine. And here we can see that for weight, yes, the solid purple line and the dashed blue line are pretty close. For horsepower, it's a little wonky, but not that far off. Displacement is a little bit of a smiley face. That is a little bit of a concern right there. But it's not that bad, so we'll go with it. Next, we'll check the normality of residuals. Oh, did we skip 2? Yeah, we skipped 2. Why? Because the second one is I for independence, which is normally something that you're checking by understanding how your data were collected. If we want to look at independence, we might just look at the data and say, well, are these all different models of cars? Yes, so we didn't measure one type of car several times. No, so these are all independent observations. Okay, good. Again, you just need to know your data. There are also tests that you can do, but most of the time we understand the experimental design. Normality of residuals. How do we check normality of residuals? Okay, there's a couple ways. One way is using the QQ plot, and the other way is using a histogram. If I run this whole chunk, I do both at once. If I look at this first panel here, what I have is a scatter plot of the normal quantiles and the residuals from Model 2. And here very nicely we have our shaded error line. And what we're looking for is that all the dots are not just close to the line, but within the shaded line, the shaded area. And we can see we have 2 points, the Fiat and the Toyota Corolla, that are outside, especially the Fiat, it looks like, is pretty far outside. That means it's got pretty high residual. It means this isn't exactly normally distributed. Our residuals are not perfectly normally distributed. And when we look at them in the histogram, again, we can see there's a slight right skew to our residuals. A slight right skew to the residuals, but not too far off. I think it's okay to proceed with the analysis, especially as we have a pretty good sample size of 32 observations. Next, we'll check homoscedasticity, or constant variance. Remember, for this, we want our line to be flat and horizontal. So if we plot Model 2 and we say which equals 3, this gives us just the third plot. We've seen this plot before. What we have here is the fitted values for the entire model with all the variables versus the standardized residuals. And again, we're looking for a line that's flat and horizontal. That line's not too far off from flat and horizontal, even though the Fiat and the Toyota Corolla have an error, a standardized residual that's fairly high, and so does the Chrysler Imperial, and that's pulling up the edges of our little smiley face here. It's not much more than a bit of a smirk. I think it's okay to proceed in terms of this constant variance assumption. Scrolling down next to outliers. Well, we already looked at a scatter plot, so we would be able to probably see any strong outliers. This allows us to more formally test it by looking at a plot of the Model 2 and then pulling out the fifth of the plots that usually come out from this command. And we can see we have this residuals versus leverage plot. What we're looking at here is to see if any of the points fall outside of these dashed lines that indicate the Cook's distance. If they fall outside of the 0.5 line, that suggests it has fairly high Cook's distance. If it falls outside of this 1 Cook's distance, that is probably cause for serious concern. In this case, all of our points are within the safe zone, so we're okay in terms of outliers and leverage. Finally, we'll go to multicollinearity. There are two ways we're going to check multicollinearity, or the independence of the x variables. I know this is new, but check it out. I think you can get it. First, we'll load the dplyr package. That'll help us to run some functions that'll make it easier. And that first thing we're going to do is we're going to make a new data frame that's going to select out of the whole data frame just the weight, horsepower, and dispersion. So it's going to make a mini data frame and store it in model variables. When we run this, you look in the upper right-hand corner, we see we've just created something called model variables that contains just weight, horsepower, and displacement. And the reason I'm going to do this is because then I can run this correlation analysis on that mini data set and get a matrix that shows the correlations between all of these three different x variables. So if you look here, you see weight is correlated with weight perfectly. That correlation is 1. It is perfectly correlated with itself. Not surprising. And then weight is correlated with horsepower. It's got a positive and moderately strong correlation of 0.65. So heavier cars are more likely to also have higher horsepower. Not surprising. And weight is also correlated with displacement, and the correlation coefficient here is 0.88. Remember, we wanted our correlation less than 0.8. This is a cause for concern. That means that weight and displacement are strongly correlated with each other, and that means it's probably not adding much more information to include both of them. They're probably affecting y in a similar way. It's like they're dogpiling on top of each other. That increases or inflates our variances. Not good for our model. Well, let's see. And we also have the correlation between horsepower and displacement is 0.79. That's pretty close to 0.8. Yeah, that might also be cause for concern, but let's check the variance inflation factor and find out just how much this multicollinearity is affecting our model. So if we run this command, simple VIF, on our model 2, did I tell you this was going to be easy? That's pretty easy, right? We run that, and then we can see the VIF for weight is 4.8. That's well less than 5, so that's okay. For horsepower, it's 2.7. Again, well less than 5, no problem. For displacement, it's 7.3. That's higher than 5, but it's still less than 10, so we probably are okay keeping this in the model, although when we do some model selection later on, we might decide to exclude this variable. Scrolling down, answer this question. Do any of our x variables show high correlations? Well, yes, right? We see that. What about the VIFs? Should we eliminate one or more variables from the model? In this case, no, but there is some cause for concern with displacement having a relatively or a moderately high VIF. So answer that question in complete sentences, please. Pause the video, do that, and then we'll scroll down to this handy function that is used to check the validity of all the models at once, or you can just watch this while you're typing the answers, because it's basically just showing you that if you install these packages and run this function called check model, you get a handy dandy nifty bunch of plots that kind of check everything for you at once and give you these nice little kind of cliff notes on what they all mean. This is checking linearity. Reference line should be flat and horizontal. In case you forget, I forget. Over here, collinearity. It says, what is collinearity? VIF may inflate parameter uncertainty. Low is less than 5. Moderate is less than 10, right? It gives you a little graph showing them. That's pretty handy. I don't like how they end up kind of squished on my screen. Maybe you can figure out how to make them look better, but it's nice that it does them all at once for you. Scrolling down, we can now start to look at the results. So to look at our output and interpret our results, run this command, summary on model 2. Boom. And now we get an output that looks kind of familiar because it's not that different from our simple linear regression. We start with the call. This is the formula we ran, miles per gallon as a function of weight, horsepower, displacement on the DAT data. And again, we get the residuals, and we can see again that our residuals are roughly symmetrical, -3 to 5, 8.8. The median is pretty close to 0, which it should be, so great. Now we go down to the coefficients table, and we can see that our intercept estimate is 37, pretty similar to what we had with the simple linear regression. This gives us also the standard error of the intercept, the t-value, and the p-value of the intercept. We then also have the estimate, standard error, t-value, and p-value for our first x, which is weight. So this is the slope of weight on miles per gallon after accounting for horsepower and displacement. And this is the standard error of that slope, the t-value, and the p-value of that slope. And we see that the weight variable is indeed significant. It is a significant predictor of miles per gallon after accounting for horsepower and displacement. Horsepower estimate is 0.03. Here's a standard error of the estimate, t-value, p-value, and we can see also that it's also significant, although the effect size is much lower than weight. Displacement, slope, standard error of the slope, t-value, p-value, we can see that our p-value is greater than 0.05, so we would not reject the null hypothesis, and we would say it does not have a significant relationship. We get the residual standard error and the degrees of freedom. The multiple r squared is 0.8268, and the adjusted r squared, which takes into account kind of a penalty for each additional variable that we add. We get the F statistic of 44.57 on 3 and 28 degrees of freedom, with a p-value that is also very small, much less than 0.05, and this tests the significance of the overall regression. And when we did a simple linear regression, it's essentially the same thing, but now we've got a multiple linear regression. Is the overall regression significant? Yes. Are the individual predictors significant? For weight, yes. Horsepower, yes. Displacement, no. So we can see that now the relationship between miles per gallon and weight is weaker in terms of slope. It is -3.8 compared with -5.34 when only the weight was considered, right? It kind of took something away when we added the other variables. The effect of weight on fuel consumption was adjusted according to the effect of horsepower and displacement. This is the remaining effect between miles per gallon and weight after the effects of horsepower and displacement have been taken into account. If we want to plot these variables, want to plot these variables, we can run this command here. This is kind of nifty. I like what this does here. No, I didn't think of it myself. I got this off the internet because really plotting 3 different x variables when they're all numeric is a little tricky. It's one thing to put your weight and your miles per gallon on different axes, and you can see as weight increases, miles per gallon decreases. Okay, great. But what about displacement? Well, the size of the dots here tells us something about displacement. The smaller dots have lower displacement. The larger dots have higher displacement. And we can also see this negative trend where we get higher displacement that goes along with higher weight and also goes along with lower miles per gallon. So displacement, even though it wasn't a significant predictor in our analysis, still has a trend of a negative relationship with miles per gallon and a positive trend with weight. Likewise, horsepower. Now here you can see the lighter shaded dots have the lower horsepower and the darker, it goes opposite. Let's look at that. The darker shaded plots have the lower horsepower and the lighter shaded plots have the higher horsepower. So here we have a lot of dark dots. these have the lower horsepower, and they are also in the area of lower weight and higher miles per gallon, right? And here we tend to have more of the lighter shaded dots, and these have either lower or moderate horsepower that tends to be associated with higher weight and lower miles per gallon. So here's a nifty way of coding your points so that you can represent the relationship between all of these variables at one time. You could theoretically also add another variable and change the shape of the dots, but that would be a lot. Remember before when we had a categorical variable, we had two different lines. Here we don't have that, right? We just have one regression line, which we could also add, but we wouldn't have two, because unless you wanted to categorize displacement into like high and low or horsepower into high low, then you would have two different categories. Then you could have two different lines. Otherwise, these are continuous numeric variables, so they have to be represented in a way that shows their continuous variation, in this case by a gradation of dot size or color. Nifty, right? All right, let's scroll down to our conclusions. Almost at an hour. Conclusions. Based on the output of our model, we can conclude that, and here I've pasted the hypotheses for you, the null hypotheses, so you can remember, okay, we're testing this null hypothesis. What do we say about our conclusion? So for that first test of beta 1 equals 0 of is fuel consumption associated with a car's weight at a constant level of horsepower and displacement, right? 1. Yes, we can say there is a significant and negative relationship between miles per gallon and weight, all else being equal. For an increase of 1 unit in the weight, that is, an increase of 1,000 pounds, the number of miles per gallon decreases on average by 3.8 for a constant level of horsepower and displacement. And our t-stat is negative 3.56. Our p-value is equal to 0.001. For our second hypothesis of beta 2 equals 0, which corresponds to testing the hypothesis, is fuel consumption associated with horsepower at a constant level of weight and displacement, we can say there is a significant and negative relationship between miles per gallon and horsepower, all else being equal. For an increase of 1 unit of horsepower, the distance traveled with a gallon decreases on average by 0.03 miles. For a constant level of weight and displacement, t-value negative 2.72, p-value is 0.011. Third, we go down to thinking about the beta 3, which corresponds to testing the hypothesis. Is fuel consumption associated with displacement at a constant level of weight and horsepower? So we do not reject the null hypothesis of no relationship between miles per gallon and displacement when weight and horsepower stay constant, because our t is only negative 0.091 and our p-value is 0.929, which is greater than 0.05, right? So we have no evidence to reject the null hypothesis that our beta 3 is not equal to 0. Essentially, the slope is 0. The slope is nothing. There is no effect. Finally, just for completeness, the test of beta null or beta 0 is equal to 0 corresponds to testing the hypothesis. Is miles per gallon different from 0 when weight, horsepower, and displacement are equal to 0? So for completeness, but it should be interpreted only when it makes sense. For a weight, horsepower, and displacement equal to 0, if all those factors were set at 0, you had a magical car with 0 weight, 0 horsepower, and 0 displacement, we can expect that a car has, on average, a fuel consumption of 37.11 miles per gallon. And that's a significant intercept, but again, doesn't mean very much since that doesn't exist. Okay, now scrolling down to the final 2 questions here, I want you to think about this and give me some good answers. What does it all mean for our goal to reduce carbon emissions? If you're the consultant for the Department of Land and Natural Resources or a nonprofit group or some company that produces cars who wants to make a more fuel efficient car, what would you tell them about the directions they should take in terms of reducing carbon emissions and making cars more fuel efficient? Right? What factors are important? What matters? How would you state that? And then think about what other questions we could ask next. What else would you want to know? You're the consultant. You're thinking, okay, so we know that, here's what weight does, here's what horsepower, displacement. What else might we want to know? We could collect more data, or we could look at some of the data that we already have. We might think, how do these other factors potentially affect our miles per gallon? Is there something else we can pull out of the data? We're looking at the data over here. We've got, maybe the model of the car. There's several Mazdas. There's a few Dodges. Maybe the brand of car makes a difference. We might want to think about, well, what else you want to think about. So I'll leave this up to you to write an interesting idea for what questions we could ask next, either using the existing data or other data that we want to collect, the price of the car, something. And that's it. So I got this in just about an hour, and our lab is an hour and 15 minutes. I hope that you can complete this all during the lab with Michelle and I there to help you answer the questions. And yeah, I hope this video is helpful for you. Aloha.
Aloha. One more thing, I almost forgot submitting the assignment. So you've gotten all the way down to the bottom, you've answered all the questions, run all the analysis, and now you have to submit the assignment, right? That can be a little bit tricky, but you know what? This time it should be okay. It should be okay. You can see I just opened it up, and without doing anything at all, I can submit the assignment just by going up here to knit, clicking the drop-down menu and saying knit to HTML. Just wait a moment while it's processing the file. And it opens up as an HTML, just like this. It automatically runs all the code, and it just shows you each place where you're supposed to answer a question. You should have your answers written in here. So if you didn't change any of the code, you just ran it, it should work to be in HTML. And then you've got it saved in the same folder where you saved your RMD. Wherever you saved that notebook that I sent you, if it's in downloads, then this HTML will be in downloads. Okay? If I close that, I can also try knit to Word. See how this works. Fingers crossed, everybody. Processing file, 46%. You can look down here, what's going on. 97%. And look at that. It knits to Word. It knits to Word. What's kind of nice about knitting to Word is it allows you to edit the file, whereas with an HTML you can't. How about I send you this file too? I'll send you this file too. So if you can't knit it, if something goes wrong, you can still answer the questions and submit your homework. Okay? All right. I've got that saved. Location, same folder. Great. Great. There's another option here I'd like to show you, knit to PDF. Now, the first time you knit to PDF, it's going to ask you to install LaTeX. Go ahead and install LaTeX. Google it. You can figure it out. You don't have to, but you could. And then you will find that you have a PDF file. Very nice, very professional. There are two options I just gave you for knitting. Oh, mine didn't work. Okay, output, let's see. A new version of LaTeX has been released. I need to update it. Okay, so I need to update this, and then I can do it. So, and let's see, it tells you where to go. See https://bookdown.org, all this. So if I put that into my browser and I follow the instructions, or here's another website I can go to for debugging, put that into my browser, follow the instructions, you can figure it out. But you don't have to. HTML is easy, Word is fine, right? And I'll send you that Word file. And I will send you this file too as an updated version because I changed some things around. Right? Hope that worked out for you. Stop share and stop recording. Got it.